There we go. Now we're recording. So for the Christmas gathering, again, it's going to be on December 10th. It's going to be held at the Rathskeller. The chapter is going to pay for dinner. We're just not paying for any type of alcoholic beverages. So if you're interested, please send me an RSVP. That way I could just have a decent count of who's coming and I can let the Rathskeller people know. Something else to think about that's coming down the pipe in February is going to be the elections. I will not be standing for re-election, so the chair will definitely be open. Doug, are you going to try to step down from treasurer again, or are you wanting to run for treasurer?
I do not want to be treasurer again.
You heard it from the man. He does not want to be treasurer
So
again.
you need to find somebody else. I mean, to everybody let people know here, a few years ago, I discovered that this chapter had like $7,000 that the Indiana state had seized. So that's the only reason I became treasurer, so I could recover the $7,000 and put it back in the chapter. And we have that. And now I've been stuck for being treasurer for the last 3 years. So you need to pick somebody else.
Yeah, so you heard it. I'm not running for re-election. Doug's not looking for re-election. Bill, you looking for re-election? Are you going to run again, or
Bill is here and will go wherever the chapter wants him to be placed.
okay? All right. So yeah, definitely think about it. If you're interested in running, let me know. I'll put your name into the list of those that are running, and then in February we'll have that election. So with all that said, I'm going to go ahead and lean into our presentation. Again, we have Mark Karwisch, who is regional sales for Telestream. He covers Indiana and pretty much Michigan and all the way south to Florida along the East Coast. And then he has brought with him Mike. If I'm saying this wrong, Mike, let me know. It's Waidson. Is that how you say your last name?
Waidson.
Waidson. I apologize.
No
Mike
problem.
Waidson from Telestream as well, who's going to talk to us about PTP. So, gentlemen, if you want to take over, you're more than welcome.
Yeah, absolutely. Thanks everyone for joining. Once again, my role and responsibility at Telestream is that of sales. So, as is always the case, I have to bring a smart guy along with me. So, without further ado, I'm going to turn it over to Mike.
Hello, everybody. Thanks for joining us today. Going to see if all of this technology works and see if I can share my screen. And
You
then
should
I
be able to
will.
share it now. I just gave it permission.
Thank you very much.
Thank you.
Okay, so I will bring that up and bring that across. So hopefully now you see my screen. And we're
I
going to
do.
go and thank you very much for confirming. And we're going to talk through precision time protocol. If you haven't already guessed, I'm originally from England, so hence the accent, or a little bit of an accent. Let's say it's halfway now between here and the UK. So if I go to England, they think I'm from America. If I'm here, you definitely know I'm from England. So. And I've been working for Tektronix and Telestream for over 25 years. And I had the privilege of working on the JT&M sort of task force, uh, developing and evaluating the PTP and 2110 standards. So we did a lot of testing of PTP, at various events and evaluating all the vendors who got together to validate PTP or 2110. So I want to go through just briefly some of the standards and the configuration pieces and to invite you to keep time with a variety of different time devices. So some of you may be familiar with Network Time Protocol, NTP. That's keeping our computers in time. And others of you may know Precision Time Protocol, keeping our video and IP networks in time using PTP. And PTP is revolved around certain standards, but I want to start out just by giving a kind of an overview of Network Time Protocol and kind of comparing and contrasting why we use PTP over NTP. So basically NTP and its version 4 is standardized in RFC 5905. There have been multiple iterations of that timing device. It's used primarily to synchronize computers to within a few milliseconds, and it's based on a client-server model to send the information for the time to each of the computers. There are various clock strata which define how well the sender of the time is locked to a time source. Typically, stratum 0 is a high precision. It's going to be atomic clock or GNSS or PTP that the device is locked to. So it has a highly accurate time source, and then it will then pass on its time information through the protocol. There are also then stratum 1, stratum 2, and stratum 3, all the way up to stratum 15. And these basically mean that they are certain levels below kind of the primary time source. So they will go to a primary time server, synchronized to within a few microseconds of stratum 0. And so they will go down in those levels as you get typically further away from that major timing source. NTP is primarily a software timestamp, so it uses application data inside the system to provide that information, to get the time, and then to transmit that particular piece, all done primarily in software. PTP, because we want more precision, uses hardware timestamps. So it's going to have some kind of hardware or configuration system or a combination of hardware and software to provide and transmit the timestamp that's within a precision time protocol. So a little bit different in the way in which it processes the data and sends that data out. So the reason for using precision time protocol, and it's standardized in IEEE 1588. That's kind of the base configuration, and it's what we call PTP version 1. Used a lot for a variety of different audio devices still, and it's also used in a wide variety of other configurations, not only power, financial applications, telecoms, a whole series of industries use PTP. And then coming from that is probably the one that most people are familiar with now is PTP version 2, standardized in 2008. And that's primarily what we used for developing the IP media network kind of times relative to PTP. And that was recently updated in 2019 to what we typically call PTP version 2.1. So a little bit of an addition to PTP in some of the standards and updates to specific applications. So we have a client server architecture. Typically we have a PTP leader, which is providing the clock source. And we have a PTP follower, which is receiving that clock source and using it to time its system or systems together. We're primarily using our hardware-based process to do those timestamps so that we can get accuracy to nanosecond or sub-nanosecond timing, which is much better than the NTP type of protocol. And we really need that in order to provide synchronization for our video through the system. It's fairly low cost and low resource. There are a lot of little kind of syntax areas and protocol particular pieces that are a little different than traditional Blackburst or SDI signal references. But it also requires a very little bandwidth in order to provide this PTP data. So we're going to be sending packets in terms of, once a second or 8 times a second for all of these different messages that I'm going to go through. So a relatively low bandwidth is required to support PTP. And that can be an advantage in some cases, but it can also mean that it's overwhelmed by all the other IP media traffic that goes on the network. So as I mentioned, IEEE 1588, the latest is 2019, is our standard for precision clock synchronization. And as I said, it's used across a variety of different industries. So power, telecom, financial applications, and of course, broadcast. And each of those typical applications tends to have slightly different variations to meet their requirements. So the IEEE 1588 is kind of the reference, and then we add to that reference to make it applicable for all these different kind of applications. So in SMPTE 2059-1, we provide the information for generation and alignment of the interface. So that defines our SMPTE epoch, which is the time when the Big Bang occurred, and that's our reference point, which is January the 1st, 1970 at midnight. So that's our time reference, and we've just been counting seconds and nanoseconds from that time. And then we get our profiles, which are specific for the broadcast application. So this means we want to incorporate daylight savings time, leap seconds, drop frames, all of the kind of things that we're specifically needing to use within a broadcast application that we can use for time code and other applications within the broadcast facility. So SMPTE 2059-2 is typically the profile for our PTP. There are a new variety of different documents that have been updated within SMPTE. The engineering guidelines is an introduction to synchronization using PTP. And then there's a reference standard, RP 2059, which is a Yang data model. And this basically says we want to use this kind of syntax and language to represent each of the kind of protocols within PTP so that we can standardize our metrics across a variety of different devices if you're going to support the Yang data model. Also, PTP is used within AES-67, so there are specific requirements to meet PTP timing within those documents. And then there's a AES R16 document, which is kind of a harmonization of AES-67 and SMPTE 2059-2. So that they can each interoperate together. PTP has a variety of different terms, so we'll start with some of the very basics. There's a PTP domain. This is a logical grouping of clocks that are synchronized to each other. So they all will be locked to a grandmaster, which is the ultimate source of time for clock synchronization. Typically in broadcast applications, that's going to use GNSS or GPS as the synchronizing source of time, and then provide its time reference to all the other devices. A leader clock is a clock that is the source of time for a specific group or domain that are all synchronized together. And then we have our follower clock, is the clock that's synchronized to another clock. So we can see that kind of architecture of a grandmaster. We can have multiple domains. Typically in most broadcast applications, it's primarily one domain that has the leader and then a whole series of media nodes that are following that PTP time. There are a variety of different messages used in PTP to communicate certain syntax. And the first of those is the announce message. This kind of establishes the synchronization hierarchy in the system by using the best master clock algorithm that we'll describe in a moment to provide us with a definitive answer to who is the grandmaster. So we'll elect a grandmaster and provide status and characterization of the system using the announce message. So it will provide us with the domain information, the priority information for priority 1 and priority 2. It'll provide information on the device, the clock class, the clock accuracy, and the clock variance. and its clock ID, which is typically the MAC address of the device. So the
Hey,
announced
Mike.
message, yes, sir.
So, thinking about this in terms of how PTP networks are set up with like boundary clocks and everything else, if you
Mm-hmm.
have a boundary clock that I guess is just repeating what the grandmaster says, if a device is reaching out looking for who the grandmaster is, will it latch on to the boundary clock as a grandmaster, or will it still look for whoever the original grandmaster is that may be feeding other switches downstream with data?
That's going to depend upon what the priority levels are for the device. So you get to set priority one and you get to set priority two. And you typically, if you're in a boundary clock situation, then you can choose priority one to be the same for all devices in the network.
Okay.
And then you will use the clock class and the clock accuracy and the clock variance. And those are usually device dependent. So a device will say, hey, I'm locked to GNSS, and that will give it a better clock class than a device that's not locked to GNSS.
Okay.
And then you'll get a priority 2 value, which you will set for the device that you want to become the grandmaster. And so, just like you would do in traditional um, reference system, you have a primary reference that's providing your analog and your digital signals, and then you might have a backup reference. So you've defined where those are in the rack, and this is my primary, and this is my backup. The similar kind of thing would happen for which device you wanted to become your primary grandmaster and which device you wanted to become your backup grandmaster. And you would set that to the lowest priority value that you would use to define that election process. Ideally, you don't want the switch to become a grandmaster. So you typically put its priority level a lot higher than you would do for your synchronization system. So you would choose those kind of configurations. But all devices that are master clocks or leader clocks can be elected um, to become a grandmaster, and so you could choose which one. The thing in PTP is rather than just a primary and a backup, you can use a third level, a fourth level, a fifth level. You can, go at multiple levels to define if this one fails and this one fails, then I'll make this one the grandmaster. So you can have an election process on multiple different levels to choose which device becomes the grandmaster. But if you don't select the right priorities, you can just put a device on your network, and audio devices typically like to somehow become the grandmaster when they get started. So they might come on the network and say, hey, I'm available, and take over. And you don't want that to typically happen. So you want to constrain the network. And typically, if you're in a boundary clock, you'll have an ability to say that these ports that are media nodes, I don't want them to become or be part of the election process, so I will make them master only so that they can never become a grandmaster, and that will resolve in some of the issues that I might have with some media nodes trying to take over. So that's one way of managing that situation. But you get to choose kind of who's in the election process and how that process works through the system. And we'll show a couple of examples as we go through. The other message to talk about is sync, and that's the important part because that can typically contains the timestamp. So we mentioned the SMPTE epoch, January the 1st, 1970 at midnight, and we've just been counting seconds and nanoseconds since that time to now. And so that gives us an indication of how long it's been since that time to now. And we'll use that as our synchronization time value that is carried within the sync message, or sometimes it can be carried in a follow-up message within the system, depending on how whether you're in a kind of one-step or two-step configuration. So you have those kind of possibilities within the network for carrying time. The other part of the messages is an ability to know how long it's taken for the message to reach the media node and how long it would take a message to go back to the grandmaster. And since those can vary in the network, we send out a delay request from the media node that will go to the grandmaster. The grandmaster will then send back a delay response. And from these characteristics of the messages that we get, we can calculate the overall delay across the network and the time difference between the grandmaster and the media node. And then we can slew that time between those two devices together. So the delay request and delay response message are important in gauging the overall delay across the network. And then we have some management messages that provide that SMPTE TLV metadata that contains information on daylight savings time, drop frame, when a jump of drop frame is likely to occur, all of those kind of things, the leap second information, all of that information is carried within the TLV management data for the SMPTE 2059-2 profile, and that helps to define certain particular characteristics for our broadcast application to take PTP and make timecode from it, for instance. There's some other messages called signaling, which provide negotiation of kind of the message rates that a grandmaster can handle. And the media node will send, I'd like to do 8 messages a second, and the grandmaster might respond with saying, well, I've got so many media nodes, I can only do 4 messages a second. So there'll be some negotiation sometimes that can happen in the signaling, but that doesn't typically happen because you usually set these values up for each of your ports and each of the configurations. So going kind of around to that best master clock algorithm to define how we make this decision process, I've kind of outlined it a little bit already. But you can set a priority 1 value. The lowest value of that 0 to 255 value will win a round of the competition, if you want to think of it like that. Then you have your clock class, your clock accuracy, your clock variance. This is set by the device itself. It's just parameters that it says, well, I'm locked to GNSS, so therefore I have a clock class of 6. If I was locked to GNSS, but I'm no longer locked to GNSS, then I'll have a clock class of 7. And so it will degrade from that value and get higher and higher depending on your configuration. So if I'm not locked to GNSS at all, then I might have a value for my clock class to be 248, which means I'm handset. I'm typically running internal in that case. So these are kind of degrees of the reference that a typical possible grandmaster could have. And then you have the priority 2 value. Again, a value between 0 and 255. The lowest value wins in those configurations. And I'll show an example of how we might set up these priority 1 and priority 2 values to perform the BMCA and choose or elect our grandmaster from the series of rounds that we would go through. So here is a typical system, and we've decided that we've got a primary and a backup system just like we would in a traditional reference with analog blackburst and SDI signals. And we've set a priority value of 10 for all the devices in the network that we want to kind of be in the first round of this competition. So this is our lowest value. Other values may be slightly higher, and so they won't take part, or they'll be eliminated, let's say, from the first round of this competition. So all the devices with a priority 10 go through to the next round. The next round is the clock class, the clock accuracy, and the clock variance. And so we look at those devices, and 2 of those devices are locked to GNSS. So they will have, or likely have, a clock class of 6. Other devices that are not locked to GNSS would likely have a clock class that might be slightly higher. So that will eliminate the lower 2 devices in this configuration and mean that the GNS devices, primary and backup, go through to the next round of this process. Priority 2 values are then set for the primary and backup, and that priority 2 value that is the lowest means that the primary would be elected as the grandmaster in this case. If, for instance, it lost GNSS, its clock class would go up slightly to clock class 7, let's say, and even though its priority 2 value was 5, it would now be eliminated from the priority 2 kind of reign because clock class round went to the backup because it was still locked to GNSS and had a clock class of 6. And then in that case, it would become the grandmaster. And when GNSS was restored to the primary, its clock class would also be 6, and so priority 2 of the primary would be lower, and it would be elected the grandmaster. So this process is a continuation all the time, looking for devices that are the grandmaster or the best master to be used, and the rest of the system, if that announce message doesn't happen from the grandmaster, then an election process will happen again. So this is our best master clock algorithm that kind of elects our grandmaster within the system. And you'll notice in this case that I have set different higher priorities for my switches. So I have a boundary clock switch that's connected to my primary and backup. So I've set its priority value to 128. So if the other 2 devices aren't really taking part, or lower level devices are referenced to this boundary clock, they can find the priority values for the switches of 128. And then my kind of least switches from there are set at an even higher priority because I don't want them to take part in becoming a grandmaster. And then on the switches and the media nodes, I can choose certain devices that I don't want to become or to take part in the grandmaster by just making them master-only ports. So that's my typical configuration for the BMCA and choosing the primary. My next kind of configuration will be to work out the overall time and message rates between the devices. So I've mentioned that we're sending a sync message. Typically, we send that every 8 times a second, and that is sent with a timestamp at T1. It makes its way through the network to the media node, and when it reaches the media node, it will get a timestamp of T2. At some time, it will then send out a delay request at a time T3 that will make its way back across the network to the grandmaster, and it will get a timestamp when it's received there of T4. At that timestamp, it will respond back to say, I've got your message, and send back another delay response. So within these messages, we've got these various timestamps that are calculating the overall offset between the time of the leader to the follower, and also it would calculate the overall delay. And so we can use a simple mathematical calculation with these timestamps to calculate the overall offset and the overall delay across the network, assuming it's symmetrical, that the path forward and reverse are the same. And that's a critical part of making the measurement and the calculation between these messages. So we can then determine the offset between the follower and the leader, and we can then slew our leader to the new time that we believe the leader is at. And we can also evaluate it based on the delay that that message will have taken to get across the network. Within our PTP system, there are a variety of different message rates that are used. So this is kind of the harmonization between 1588, 2059, and AES 67, that typically we have one announced message sent per second, and the timeout is 3 announced messages. What that means is if the announced messages aren't heard every second in our time period, we'll wait 3 missing announced messages before we'll start the BMCA process. And then we'll go through it and find another grandmaster. So we have a timeout that typically is set to 3. Then our sync messages are typically sent at 8 messages per second. And in our system, delay requests and delay response are calculated based on that kind of message rate for sync. And so typically they would follow that and be 8 messages a second also. And then we can choose our domain. The standardization for 2059, the kind of default value is 127. And for AES 67, it's a 0. Typically, we don't recommend that when you set up your network, you use the default value. We recommend you use some other value. And the reason for that is that if you set the default value and you put a new piece of equipment in it, there's a potential that when that device gets connected immediately to the system, it could, with its different priority values, decide to take over the network. And so you don't want to kind of do that within your configuration and disrupt who's the primary and who's the backup. So we typically recommend that you do some configuration to your media node to set it up so that it can then go on the network. Now, that doesn't prevent you from using the default 127, but just be aware that if you do use 127, you better make sure that when you connect your device to the network, that you've done all your configurations before you make the connection to a port. Within PTP, there are a variety of different ways of sending the messages. So we can send them unicast, which is basically our one-to-one communication. We could potentially send them as broadcast, one to all, but most cases we're sending them as multicast with one-to-many. And so our typical address for the PTP is 224.0.1.129, and we'll send the information along that multicast. Because IP is all about handling and how well we handle the messages and constraining the traffic across the network, you can use a mixed-SMPTE communication model, which sends a combination of unicast messages and multicast messages across the network. So in that kind of case, typically we'll send certain messages like announce, sync, follow-up, and management as a multicast because we want every device to receive those messages. But delay requests and delay response are kind of more one-to-one communication. So rather than sending delay requests to everybody who's subscribed to PTP on the multicast network, we will send just a request from the media node to the grandmaster in unicast. So that limits the amount of traffic that we have to send from all of these media nodes that potentially has to be handled or thrown away by all the other devices that don't want that message. So mixed-SMPTE is this combination of unicast and multicast, and so delay request and delay responses gets typically sent as unicast messages, and the rest of the messages get sent as multicast because we want everyone in the network to hear those that is subscribed to PTP. Within our configuration, it's a good idea to kind of set these configurations up so that we have our primary, we have our backup. We might have 2 switches, again, a primary and a backup for our 2022-7 configurations. And so in those configurations, if you do that, obviously you might want to cross-link your connections between your primary and backup configurations. So you can cross-link them so that primary gets to go to the backup switch as well as the primary switch and vice versa. And we also typically recommend that there's a PTP message link between the two switches so that um, if they're negotiating between the PTP messages they get, you don't get the primary going to the primary switch and the backup going to the backup switch only. You should theoretically have the primary master clock being chosen on both switches so that they both have the same PTP rather than a backup and a primary configuration for time. So we typically have a link between the two switches to provide that communication so that we can choose one overall grandmaster in our network. And then our media nodes that are connected to both the primary and backup should choose the appropriate one that is valid in their configuration, and they should both be driving from the same grandmaster clock in those cases. So the configurations and kind of the best practices that we have within our configurations is to make sure that we have a solid network configuration for our media network and a solid foundation for PTP. So in these kind of cases, you need to establish a suitable network, and you need to make sure that you've put in different types of configurations. So we've heard mention here of a boundary clock. So a boundary clock is a configuration where a boundary is created between the switches. And so if we have our boundary clock here in these kind of configurations, it means really the PTP messages are just communicating to the switches in the network, and depending on where your architecture is. So this creates a boundary. So it makes the grandmaster have an easier life because it's only going to be talking to a few switches in the network, and the rest of the media nodes are going to be talking to the switches themselves that are sending the PTP protocol out based on this grandmaster. So we create a boundary, which means that not all of the media nodes are corresponding with the grandmaster. It's only the few select switches that are boundary clocks that are communicating with the grandmaster, and this means the overall message flow between the grandmaster and this series of switches is relatively low. So there's not hundreds and hundreds of media nodes communicating with the grandmaster, or thousands and thousands of media nodes. So we constrained by using this boundary clock a way to give the grandmaster an easier life and only talk with a few devices and communicate effectively with those devices. And then boundary clock switches take that information from the grandmaster and convey it to all the media nodes that they are serving within the network. So the media nodes are really only communicating in most cases with one switch port to provide their PTP. So they've got more of a direct connection in that case to the PTP messages that they're going to send.
And Mike, correct me if I'm wrong, but you see a lot of boundary clock use in like leaf and spine network architectures, correct? Or do you see them across all of them?
So the boundary clock is a very good thing to have in your system, and it makes life in most cases a lot simpler. So our kind of recommendation is to use a boundary clock everywhere that you can.
Okay.
There may be cases where you decide that I don't want to do that. Maybe you're trying to harmonize your video and audio network, so you've got completely separate network for audio than you do for the rest of the media. So you might create kind of a star kind of configuration where PTP is serving this side and another network within those particular configurations. But using a boundary clock is a great way to make the grandmaster easier in communicating with only a few devices. If you don't use a boundary clock in your system, then that means that every media node that's connected in the network is likely going to send its delay request message to the grandmaster. And therefore, then the life of the grandmaster becomes much more busier because he's now not responding to 10, 20 switches. He's now responding to all the media nodes in your system. And so in that case, it can become more difficult for the grandmaster to handle all of those delay requests. So in those cases, it can become more of a strain. So devices might be able to say, well, I can handle 500 media nodes, and then, the port on my system is going to flood because I just can't respond immediately to all of those messages. So there's going to be additional delay that might happen within, storing those messages and being able to respond to those messages. So if you do have no boundary clock, then every media node is going to want to communicate with the grandmaster, and so the loading is going to be more, even though that those messages are only, let's say, 8 messages a second, a relatively low rate. When you multiply that by the number of media nodes that you have in the system, then that becomes a larger and larger extent. So a boundary clock is a good thing, and using it everywhere in the network can simplify configurations. The problem in using a boundary clock is that you have to do configurations for each port on your switch that's talking to a media node, and you have to configure your switch appropriately for the domain, the message rates that you're going to be using. So there's a little bit more work in configuring the switch, but that work is well worth doing. And then it's important when you do configure the switches that you kind of establish, generalized rules that you're going to use 1 announce and 8 messages a second for your sync, delay request, delay response, so that you can use that over the whole networks, kind of standardize on a kind of process. Because potentially, if you decided that, this device over here was using 2059 and it's sending 4 messages a second, well, that's a different rate than the 1 announce message per second. And you potentially can have BMCA start to be initiated because, oh, I'm now at a rate of 4 messages a second, and after 3 announce messages, I didn't receive an announce, so I'm going to then start the BMCA process. So you can get kind of in a little hiccup in those cases. So it becomes important to have a good strategy for what your message rates are and to be consistent with those message rates whenever possible across the network. So a boundary clock is a good thing. The other thing that's used sometimes in network is a transparent clock. That's slightly different in that it just accounts for the network delay across active devices. So it still requires all devices that are partaking in PTP to respond to the grandmaster and send its messages, but it also accounts for the queuing. So if there was a delay in getting all of your messages back to the grandmaster, that information would be stored within a correction field, typically in the message, and that can help in defining what the overall queue was within the network. So sometimes you might use a transparent clock, and then other areas you would use a boundary clock. But in most systems that I see, I would say 89% of them are using a boundary clock, and that's a good thing to do within the system. The other part to the system is making sure that you're primarily using PTP version 2 wherever possible, and try to avoid using PTP version 1, even though there's still a lot of audio devices that prefer to use PTP version 1 within those configurations. And then within the system, it's possible that you might consider using it across a network from one side of the country to the other. And our recommendation in those kind of cases is each site should have its own active GM, because you can't guarantee on the forward and reverse path being identical in a wider network. So typically the recommendation is to have each site linked to its own GNSS reference and timed from that Sky reference to all devices and the local configuration. Any other questions?
I don't have any other questions. Anybody else got any questions regarding this?
Well, this is Doug. I don't, but it was a good presentation.
I was gonna say for me personally, like, you know, I've had a lot of experience with baseband and HD SDI and all that, but the 2110 world is a little new to me. But this has been very helpful in trying to understand, like, because I work in integration, so when it comes to putting these things together, how something like this can kind of works into the infrastructure and the environment. So no, thank you very much, Mike.
Pleasure.
Yeah, just so everybody knows, I went ahead and posted a link into the chat from HP. It's about leaf and spine architecture in case you're not familiar with it. It is something that I do see commonly used in 2110 deployments a lot. There was a reason why I asked Mike the question about the Grandmaster. And just so in case anybody else uses analogies like I do to memorize stuff, the analogy I used for Grandmaster and boundary clock was manager and assistant manager. The manager tells the assistant manager what to do, and the assistant manager relays it to everybody else. So I always think about the boundary. So I always remember the boundary clock as the assistant manager getting orders from the manager and telling everybody else what to do.
Mm-hmm. Yeah, in a leaf and a spine network, it's going to. So in those kind of cases, it then depends on where you put your grandmaster. So typically, PTP, because of its low message rate, might run on a 1G port, or it might run on a 10G port. And so you don't want to use, a spine port to carry that kind of data. There are switches that have that capability that will have a smaller, lower data rate port amongst all of their 100G or higher data rates on their spine port. But typically in the spine, you don't want to have your lower data rate being wasted on a low data rate port. So typically in those cases of a spine and the leaves where you've got your 25G or 10G port configuration switches, 48 port going to your 100G spine or more, then in those cases you're going to place your PTP on the spine, right? So when you place it on the spine, that's fine. It's going to then send it and send that message out throughout the rest of the network. But what you have to bear in mind is there's also a ripple kind of flow through the network when things change. So if you have a leaf that has what as your primary SPG, and another leaf over on another part of the network that has your backup, when let's say your primary disappears as the grandmaster, it's been sending all the announced messages, it doesn't then send any, then the switch that is part of that leaf will recognize that first and say, hey, I don't have a grandmaster. I need to start a process of looking for one. And I don't see anyone else around here, so I will nominate myself. So what happens is the switch will then become the grandmaster. And then it might be rippling out those messages. Hey, we don't have a grandmaster. I become the grandmaster. That message is ripples out through the spine to the other parts of the leaf. And over on the other side is the backup SPG that has still GNSS and is sending out messages and says, I can become the grandmaster. So that then becomes the grandmaster on that specific switch. It sends it across the network of the spine, and then the switch at the other end of the system will recognize, hey, there is another grandmaster out there. I'll change from being the grandmaster to this one over here. So there's kind of a ripple effect that can happen in a leaf spine architecture, and it's important to be able to evaluate that within your system architecture for when these changes happen. So one of the things that I would recommend in all of these cases is as you build out your system architecture, is being able to test that architecture out as you go forward. And typically, we like to try and break things if we can to see what happens when they break, right? And that's a good example of what to do relative to PTP as you build out your system. So one of the simple things to do would be to change priority from your grandmaster to the backup. So you just change your priority value to a higher value so that the backup changes, and you can see what happens as the backup is elected the grandmaster. The next particular part would be to disconnect your cable from the grandmaster, because it will have a different effect on the network with the port going down and how the rest of the network responds because of that. So that's another way to evaluate what happens. And so you'll take and disconnect it. You'll see how long it takes to ripple through to have the backup take over. And then after letting it stabilize for a while, you'll reconnect it back up again, and the process should follow back the other way. And then if you really want to break it and you're in a 2022-7 network and you're receiving PTP from both sides of the network, then in an extreme case, you would want to take the power and completely shut down your primary to make sure that your backup remained online within the system. So those are kind of things that would be recommended to do while you're evaluating the system design within the configuration, so that you know what happens or what can go wrong as you build out these PTP systems, and they may be slightly different per the different architectures that's used. So it's always advisable to know, how to break it and what happens when it breaks. One of the things that's slightly different relative to analog versus PTP is, I can take my scope and I can connect my blackburst reference and I can see what level it is. If it's noisy, if the amplitude's the right size, I can see those kind of things. It's much easier to see those when it's an analog reference than it is to see those things happen when it's PTP. And so you're going to have to rely on the metrics from the switches, and there's a lot of commands that you can do to get information from the switches on what happens, and then various devices like media nodes will show you what happens in those kind of configurations too.
Perfect. Thanks, Mike. We appreciate the presentation, giving us all the information on PTP. So at least now all of us have a good understanding of it. Before we call it a meeting, Mark, is there anything you wanted to throw in here real fast? Since you're the regional sales rep, I'll give you a couple minutes here to talk if you want to.
Actually, not really much to say other than obviously you can reach Mike or myself if you have any further follow-up questions. Our emails are basically just our first dot last name at telestream.net. We're always available to help you should you need any configuration help or assistance. We're always available, so please don't hesitate to reach out to me. with sales related questions. And I can always operate as a, if you will, a traffic cop to help get you to the right engineer inside of Telestream to get you the answers that you need. But gentlemen, thank you so much for your time this evening, and truly appreciate your time as well, Mike. And then most importantly, to the SBE chapter, we're always happy to participate and help where we can.
Well, thank you, Mike and Mark. We both appreciate you guys taking time this evening to come in and talk with us.
Pleasure. Thank you for the invitation.
You're welcome.
All right.
Happy to do it.
All right, that's it, everybody. Thank you for attending. I'll post the recording of this to the webpage as soon as it gets done recording and it uploads. So hopefully that'll be quick. But otherwise, yeah, it'll be available out there to watch. Anybody who missed it that may ask questions, you can point them to the direction of the chapter's YouTube page, and this video will be here. All right, thanks everybody.
Guys.
Okay,
Thank you.
thank you. Bye-bye.